Hello, good morning everyone. So as stated, I will talk about the field of wearable robots. So the idea is how to attach robots to the human body and to extend human physicality, making humans faster, more efficient, and stronger. So the field of wearable robotics is really about the science and engineering of extreme interfaces between the human body and machines. So today I'll talk about three such extreme interfaces. One is dynamic. How do you build a robotic limb that behaves like its biological counterpart? Another extreme interface is electrical. How do you have electrical information going from the human body to the external robot and from the external robot back into the human nervous system? And finally, how do you attach machines to the body mechanically so it's comfortable and healthy? So here's a video of current state of the art. This is a US soldier that was hit by a blast near Baghdad in the Iraq War. He's missing 3 limbs, an arm and 2 legs. This is progress. He's not in a wheelchair, but it's also not efficient high-speed ambulation. So as a field, we need to do a better job for this individual and many persons like him. So here are data showing 2 of the dominant problems that persons with prostheses experience. So in blue is the net metabolic energy cost to walk, and in purple is the preferred walking speed. So you see here's a person with biological legs intact, and as the amputation goes more and more proximal in the leg, so this is below knee amputation, above knee amputation, and so on, the energy consumption goes up and up and up, not surprisingly, and the speed goes down and down and down. So the higher the amputation with conventional technology, the greater is the metabolic cost, and the slower it is that a person walks. So the compelling need is, just as an example, you have the human anatomy from the knee down, a very complex neuromechanical structure that's currently being replaced for the most part with carbon composite structures that store and release energy with each step. So you're trying to emulate this complex anatomy with a piece of carbon. And orthotically, or in the brace world, this complex anatomy is trying to be augmented with often a piece of plastic. So because these mechanisms do not capture biological dynamics, because the extreme interfaces between the machine and human are not yet adequately sophisticated, you have secondary disabilities. So a large number of leg amputees have low back pain, have severe hip and knee pain. For example, knee arthritis is a dominant issue. Because it's painful to move, you have decreased vascular function, increased obesity, and all this, of course, affects quality of life. It also is very, very costly for society, costing society billions of dollars. So the idea that I will present today is, can we imagine a world where we have very sophisticated robotic structures attached to the human body that actually emulate the functionality of the human body? And if we do that, could we improve metabolic energy, walking speed, stability, and joint stress compared to conventional passive and quasi-passive devices? So to do this, we have to have a deep understanding of how we as humans work. How do we stand? How do we walk? How do we run? What are the muscles doing? What are the tendons doing? How are the muscles being controlled? If we can deeply understand these dynamics, we can better understand how to emulate the dynamics in synthetic form. So here's a forward dynamic model of human walking. You see the balls firing. That's when the model's muscles are being activated. So such models really inform the hardware and the software of the electromechanical design of these wearable robots. So a dominant project in my MIT research laboratory and in my company iWalk has been to develop a powered ankle-foot prosthesis. This prosthesis is motorized, has a motorized ankle, and has several microprocessors and about 12 sensors on board to allow it to adapt to different speeds and terrains. So here are data showing the performance of this bionic limb compared to a normal biological intact leg. So here in plot A is the ankle angle when the foot comes off the ground, or toe off angle versus walking speed. The shaded region is mean plus or minus standard deviation of what a biological limb does. And of course, the blue diamonds are the bionic limb. So we have good agreement there. Plot B is ankle work, how much energy is injected into the walking cycle per unit body mass. Again, the shaded region is biological. You see we're actually doing excessive work at low walking speeds. That was a bug in the code, and we've since fixed that bug. And C just shows that the faster the person moves, the greater is the net propulsive work. So conventional prostheses don't add any net energy. They're just springs. So this is a powered ankle, so it actually motorizes the walking gait cycle. So because of these normalized mechanics, we can reduce how much food energy a person requires to walk. So the blue data are the bionic limb. The green data are from an age, weight, and height matched persons with biological limbs. And the red data are from a conventional passive prosthesis. And we see no significant difference between a person wearing a bionic limb and a person with a biological limb. In B, we show a normalized walking speed. So for the first time in history, this is a bionic limb that normalizes speed and metabolism. But the dominant clinical story of wearable robots for the legs is stress, in my opinion. So if we look out 10, 20 years, and we're talking about the legacy of robotics in this space, it will be about that robots allowed people to walk normally with limb pathology, and that reduced stress on the back and the joints. Again, there's all these secondary disabilities, low back pain, knee arthritis, that are common today. So how it works is if the robot applies very, very high mechanical powers in this trailing leg, it reduces the stress on the leading leg. And that reduces the chance of joint arthritis. So here's a lady who is a quadrilateral. She's missing all 4 limbs. And on your left, she's wearing the bionic limb. On the right, she's wearing a passive limb. So you can see the dramatic difference in speed and the distance she's able to move in a fixed amount of time. On the left, she's a community ambulator. On the right, she really can't leave home effectively. The device also allows for fairly impressive athletic endeavors. Here's a gentleman running up a steep, rough terrain with 2 of the bionic limbs. And it also has deep emotional impact.
Oh my God. Oh my God, I can't believe it. It's just like I've got a real leg. Now don't start running.
Now turn around and do the same thing walking up. Walk up, get on your heel to toe like you would normally just walk on level ground. Try to walk right up the hill.
Oh my God.
Are they pushing you up?
Yes, I'm not even, I can't even describe it.
It's pushing you right up.
So it's interesting, if we fit 10 people, 5 people start weeping and crying. The other 5 just start giggling. And it's very common for a person to say, I have my body back. I have my limb back, which is really interesting from a human-machine perspective, because these people don't view this limb as a tool, like a hammer is a tool. They actually are starting to view it as part of their body, which is very interesting. We also build robotic structures that wrap around limbs that exist, biological limbs that exist, but have some form of pathology. So this is a gentleman that has suffered a stroke And you can see on his left side, he's hitting the ground with his forefoot instead of his heel because of a muscle weakness in the anterior compartment of the leg. This is the classic drop foot pathology. So it turns out if you build a robot, the robot wraps around the impaired limb, pushes on the human body, you can largely restore symmetry between left and right sides and the ability to walk at high speeds. The need here is profound. This individual, even though this is a crude prototype, he begged us to take the crude prototype home. He said, I at least want to walk around my house normally and then just plug the damn thing into the outlet. More ambitiously, you can think about wearable robots that span the entire leg. So this is a device that's elastic. When the foot's in contact with the ground, there's a synthetic compliance in parallel with the limb. When the foot comes off the ground, the structure becomes loose, compliant, and the biological limb is able to move. So the biomechanics of hopping and running are that the entire biological limb behaves like a spring. So we've tested this device metabolically for hopping, and we show very large reductions in metabolic cost. And now we're pursuing a device that's augmentative. So this individual does not have a leg pathology. When his foot strikes, the exoskeleton stiffens and becomes a giant elastic spring. And when the foot's off the ground, the device goes to zero stiffness. And he's able to achieve foot placement. So our vision is that in the future, you'll routinely see people running down the road, jogging, wearing robots. Why? Because they want to prevent joint injury, or they already have a joint injury, and they want to slow the degradation of the soft tissues, and hopefully avoid a total knee or hip replacement. So that's one extreme interface. The next is electrical. So can we think about neural implants where we have a direct connection between the human nervous system and an external robot? For a peripheral bidirectional system, there's two parts that are critical. One is, can we design an implant that goes into the muscles of the leg that measures the electromyographic signal across the muscle and communicates that wirelessly to an external device as a motor intent measurement? Another part is, can we communicate to nerves? So obviously when a limb is amputated, nerves are amputated, key nerves are transected. Many times nerves are mixed nerves. They have both motor information coming down from the spinal cord and sensory information going up to the spinal cord. So in principle, if the field develops an interface to transected nerves, we could close the loop between humans and machines electrically. So what would one do with a signal if one had the device? So this is an amputee walking down steps. When the foot's off the ground, the robot's under neural control. So the person's firing their own muscles, that's being recorded, and the device then plantar flexes. So the amputee sees the steps with his eyes or her eyes, decides to point the toe down. Why? Because she wants shock absorption. So it's tapping into the eyes and ears of the patient. In terms of nerve interface, my laboratory and a few laboratories around the world are thinking about how to connect to the transected nerve. A very interesting approach is to put skin and muscle cells from the person that requires the device right proximal next to the transected nerve. The nerve then grows again, attaches to those cells. The body then vascularizes the cells that have been put in, and you end up with a very stable, viable implant. Then from the muscle slivers, since muscles amplifies the nerve signal, you can collect motor information, and from the skin cells you can stimulate through that pathway to reflect pressure or force sensing on the external robot. So the amputee in the future can feel the device to some degree. So we're doing experiments with this approach. An initial experiment we did is in an animal model. We put in skin cells and muscle cells from the animal, and the nerve grew again attached to the cells. The body of the animal vascularized the tissues, and we got very, very good signals from the implant. And at 12 months out, 24 months out, the implant was completely viable, not rejected by the body of the animal. So I'll finish up with mechanical interface. So if you ask prosthesis users, brace users, what's the #1 technical problem they want solved? Probably all 100% will say, the damn thing hurts, can you fix that? I have 2 artificial legs that I'm wearing now, and I'm in a little bit of pain standing here. To me, this is unacceptable because the science and technology exists to solve this problem. So one problem with the field is that there's a very limited data set that describes the biomechanics, the anatomy of the part of the body that you're trying to attach the robot to. Typically, only shape is measured of the biological limb. That's insufficient. You need a lot more information to have a chance of having a comfortable interface. So we're developing the mathematics and the tools to change the methodology of robotic attachment. So this is just a plot of the skin strain field. So we have a methodology of mapping how the skin moves when you flex and extend your joints in your body. So this is the knee, and you see about the patella, there's a hot spot. The skin is stretching around the patella when the knee is flexed. And you can see up here that the skin is stretching in the circumference. So maps like this tell us that the interface has to move like the skin moves, or there's going to be tremendous shear forces on the skin and discomfort. You can also scan the residual limb, obviously, using modern day scanning procedure. This is an MRI, actually, of my leg. So here's my little fibula. I'm amputated here. Here's my tibia, my patella, and my femur. Sorry, this is my patella, the femur here. So such MRI data, we can use modeling to come up with how stiff the body is for orthogonal deflections of the body. So when you push on my body perpendicular to my surface, how stiff am I? You need to know that in the interface. So this is just a map of how stiff I am. So where it's red, I'm soft, and where it's most green, I'm most stiff. So we then build interfaces using 3D printing strategies where we spatially vary the impedance of the interface. So where the body's stiff, the interface is soft. Where the body's soft, the interface is stiff, and everything in between. And we've already shown very large reductions in peak pressures when a person walks. So that's spatial impedance variation in the interface. We also are looking at temporal impedance variations. There's fantastic modern materials. This is one coming out of SRI International. This material stiffens under a voltage control. So it goes from being very floppy. When you apply a voltage, it becomes very, very stiff. The power to do this is very, very, very low because it's an electrostatic approach. So I'll put a period there. So we're beginning to see glimpses in the field of wearable robotics of augmentation. So this is Amy Mullins and myself sporting bionic limbs. So for myself and for Amy, probably in 5 to 10 years, we're going to see augmentation with our own bodies. We're going to be able to walk with less energy than a person with biological limbs. This should be achievable, right? Because the bionic limbs have their own power supply. They have their own batteries. They don't have to be fueled by food energy. And as neural implants become more and more advanced, Amy and I will see additional levels of augmentation. When we're 80 years old, our balance will be superior to a person with biological limbs because robots are really fast and can respond with very little delay. So it's an exciting time because it used to be that wearable robots will vary behind the curve technologically, and now they're moving forward at an incredible acceleration. Thank you.
Thank you. Thank you very much for this very nice talk and the amazing results you have presented us. Results that address all the aspects of the prosthetic, from robotics to mechanical interfaces, and really interesting. So, some question in the audience to Hugh Herr about this talk?
Alain Belly, Laboratory of Exercise Physiology from Lyon Saint-Étienne. I would like to know if your parallel device, passive parallel device for running, reduce not only the energy cost of bouncing, but the energy cost of running.
That's a good question. Yeah, I'm sorry for the limited time. There's very little technical content in my talk. Sorry about that. As I noted, the metabolic cost of bouncing we've reduced. For running, we've not had a net reduction. So if you run without the exoskeleton and measure the metabolic power, you get the same number when you run with the device. So at least it's carrying its own mass. So we're just knocking on the door of augmentation. But one point I'd like to make is, if we have the same energy, but we're able to reduce joint stress, we have a device that may be useful in society. So I do think in the next design iteration, however, that the costs will be reduced. Thank you. One more question.
Question, Mr. Monto.
Well, André Monteau from TESAM. First of all, thank you for this marvelous presentation with so many interesting things inside. I well understand what you explained about sensors, actuators, and so on. I've still a big question mark around the energy for your systems. What do you use? Do you use batteries, and how long do they last for the people? Is it a few minutes, fewer hours, days, whatever?
Right, so all the systems I showed today are electric. So the power supply is a battery, a lithium polymer at the moment. So we use some tricks to make the system more efficient. And the dominant trick is using elastic energy storage. So we use parallel compliance, series compliance to the motor and transmission. And if you tune those compliances correctly, you can reduce the energy requirement from the battery. The bionic foot ankle is doing peak powers of 800 watts mechanical and does a net mechanical energy input per step of about 20 joules when a person walks fast. So it's a lot of energy. So from our onboard battery, we get about 2,500, 3,000 fast walking steps. The battery is modular, so a person, if they're going to walk a lot each day, they just take a spare battery. It's like a power tool. Yeah. Thank you. Thank you.
Okay, thank you very much for this talk.